So today topic is neighboring group participation. So this is nothing but it's a SN2 reaction. So we know that if we have a living group here, in case of SN2 reaction, so the ligand, which is the nucleophile, will approaches from the opposite direction of the living group. So the product will be this. Imagine this is A, B, C. So A and C will not change their position, only B will change their position. So this is the SN2 reaction. So but when neighboring group participation is there, in that, so generally we see that here we have a like inversion of configuration. From the reactant to product, there will be inversion in the configuration. We will see that. But when there is a neighboring group participation, in that case, the major product will be the retention product. Whatever the configuration is there in the reactant, the same configuration will be there in the product side also. This is because the neighboring group participation means we can say is double SN2 reaction. So in this case, there are two SN2 reactions are taking place. Okay, so now this can be, the neighboring group can be where we have electronegative atom like NH2. This can act as a neighboring group, and oxygen, and any electron withdrawing groups. All these can act as a neighboring group. They can involve in the neighboring group participation. Even carbon CC double bond and C triple bond C also can involve in the neighboring group participation, and even sigma bond in case of norbornene. Here the sigma bond is acting as a neighboring group participation. So this is some introduction about the neighboring group participation. Now we will see the examples. So here we have two examples. Here iodine we have, and OBZ. Iodine and iodine, here we have equatorial, and OBZ is at the axial. So here just remember, in case of cyclohexane, if two groups are anti to each other, or we can say diaxial, in that case the neighboring group participation will be higher. Okay, so because then only it can involve in the neighboring group participation. Imagine that this is leaving from here. So now here we have positive charge, and this iodine, here positive charge we have, and it's coming from equatorial, because this is SN2 reaction, right? So the leaving group is going from the axial position, and here iodine is acting as a, here we have two types of nucleophiles. One is internal nucleophile and external nucleophile. So in the first step, internal nucleophile comes and attacks to the carbocation, and here the internal nucleophile is the iodine, and here the leaving group is going from the axial position. That means since it's a SN2 reaction, it has to come from the opposite direction. That means it comes from the equatorial. This like this. Okay, now the second SN2 reaction. Now the leaving group, now here leaving group is this. Okay, so it is going from the equatorial. So second SN2 means it has to come from axial, and this is the way, this is the mechanism where in the where neighboring group participation is there. In those cases the configuration will be retained, and when you take this compound, here it goes only one SN2 reaction, because hydrogen, since iodine is in equatorial position, it will not having a 180 degrees to to involve in the neighboring group participation. So because of that reason, it goes a normal SN2 reaction. And now the nucleophile comes from equatorial, because only this is a SN2 reaction. So you see, in this compound we have seen a retention of configuration, okay, but in the second compound we have seen the inversion of configuration. So in the first one we have a 2 SN2 reaction, here one SN2 reaction, here another SN2 reaction. First SN2 reaction, the nucleophile, internal nucleophile is coming from the equatorial. The second, it's coming from the axial, because nucleophile will come from the opposite to the living group. So that is the concept. And sorry. So wherever neighboring group participation is there, that will be faster in the reaction. So if you see the reactivity order, so 1 will be faster compared to 2. So this is the reactivity order. And similarly here we have 2 more examples. OTS and OAC, and the second one will be OTS, OAC. Here also same, here also same. These two are, this is below the plane, means below the plane, and this is above the plane, OAC. So here they are opposite to each other, so here neighboring group participation is possible, and in this case, like, they both are same direction. So here neighboring group participation is not possible, that's why it is a slower in the reaction. So I will show the mechanism for this also. Here we have OTS, OAC. So tosyl group get eliminated here. Now there is a positive charge, and this oxygen will coordinate with this. Okay, so this is leaving from the sorry, this is leaving from the back side, and this tosylate, this oxygen coordinate from the front side. Okay, and in the second SN2 reaction, here the nucleophile is acetate, so that comes from the, since this is above the plane, and this should come from the below the plane, so that way the configuration will retain. Okay, so this is the mechanism. And when we have a cis compound, so this will be slower in reaction, and here we'll get a inverted product. So, and we can see this neighboring group participation in case of alpha hydroxy carboxylic acids also. Like this, when we have this compound, it's upon treatment with HBr, so this is leaving, here positive charge will come, and this oxygen will coordinate with this one. Okay, so this is going from the above the plane, that means this oxygen will coordinate from the below the plane, like this. And now the nucleophile, imagine nucleophile is Br minus, since this is the below the plane, here now this will be the leaving group, this bond will be the leaving group. Since it is below the plane, and Br minus comes from the above the plane, so this will be the product. And similarly we have another example here, NH2, and this is upon treatment with HNO2, NH2 converts into N2, plus. So after leaving this one, so again this oxygen attacks to this, imagine OH minus is the nucleophile here, So this is about the alpha hydroxy carboxylic compounds. And here we have three examples. This is the one. This is the second compound, and this third compound. So if they ask the question which one is, if they ask question which one is faster in the reaction, so here we have to see about the neighboring group participation. So here we have a nitrogen, and here also we have nitrogen, but here we don't have nitrogen, so this will be least reactivity. Okay, and compared to in these two, if you see in these two, here it can form a neighboring group participation, but it will not be that effective, because like here, see this one, here the chlorine goes, now NH2 comes, and this lone pair goes from here to here, and now they give the numbering 1 2 3 4 5. So this is forming a 5-member ring. So we know that the 5-member ring is angle free strain, ring free strain molecule, and OH minus comes, and this will attach to this, and this bond goes like this, and finally we'll get this compound. Okay, so the order will be 1 and 2 and 3. So why first one is more reactive than second one? Because in the first one we are getting a 5-member ring. This is a ring free strain free molecule. And this is about the nitrogen. Now we are going for the oxygen. So oxygen one is very important. So there are four examples we have. The first one is this one, OTS. The second one is like this. And this is third. This is the fourth. Now the question is, we need to identify which one is the more reactive here. Okay, just connect oxygen with this carbocation everywhere. It's very simple. And just now they give the numbering 1 2 3 4 5. Similarly 1 2 3 4 1 2 3. So we know that a 5-member ring is more stable than 4-member, then 3-member. So this is the order, right? So where stable neighboring, I mean, like, so in this fourth compound we are getting a stable 5-member ring, right? So this is more reactive. So now we have a next order goes to 4 and 3. And what about 1? So actually the next priority goes for 1, is more reactive, then 3 and 4, because in these two cases we are getting a very highly unstable strain molecule. So because of strain molecule, this is a less reactive. Okay, because of strain, we are getting a strain molecule. Because of that reason, these two are less reactive, and the first reactivity will be a 5-member ring, then this first one, then third and fourth one will be the highly strained molecule, that will be 3-member ring. So this is about the oxygen. And we have another concept, anchimeric assistant. Assistance in bicyclic compounds. So this we'll see mainly in case of non-Brownian system, and here the sigma bond act as a neighboring group. Okay, and here before going into this, we have to talk about the two things. First one is classical carbocation, the second one is non-classical carbocation. So classical carbocation means normal carbocation, the valence will be +3, here the valence will be +5. And the second important point is, if the C double bond C is there next to C plus, so this will be comes under the resonance. But in case of this non-classical carbocation, if double bond is there, that comes under the conjugation, like this. Means this will be conjugation. This forms like this. So these are the two differences we have between the classical carbocation and non-classical carbocation. And this in anchimeric assistant, we see a non-classical carbocation which is having a valence of 5. And we'll see two examples here. So here we have two examples. OBS. Just remember, anchimeric assistant means a W shape. Okay, so where we will achieve W shape, there anchimeric assistant is possible. See, here we have a W shape, means including this hydrogen, we have a W shape. This is a W shape. But here we have a U shape, or you can say, you can take this also. So there is here W shape is not possible, but here W shape is possible. Okay, that means here anchimeric assistant is possible. Okay, we'll see what is the mechanism here. Initially this bond, this leaving group gets eliminated, and there is a positive charge here, and now this bond. Okay, so just remember, whenever you are giving a number in case of bicyclic compound, you should start from the fusion point, this point. Okay, so this will be 1 2 3 4 5 6 7. So there may be a possible question, so which bond is involving in the neighboring group participation in case of bicyclic compounds? So the bond between C1 and C6 is involving. Okay, so this bond goes from here to there, and now we have a non-classical carbocation. This is the like this. So here the valence will be +5, and now we have a acetic acid. So this acetic acid approaches this one, so exclusively we will get a this product, and other product also possible, but this will be the major. So other products are this one, and these are the other products. Okay, exclusively here we'll get a exo, means in the major amount, whereas here anchimeric assistant is not possible, and here we will get a these two product major, and plus, and this product will be very less, about 7 percentage. Okay, in case of this compound, because of anchimeric assistant we are getting extra product major, but here no anchimeric assistant, because of that reason we are not getting. And in case of bicyclic compounds, the double bond also can act as a involved in the neighboring group participation. So I think this question asked in a GATE exam this year. Okay, so among these two, so in this compound we have a double bond, and here also we have a double bond. So which double bond will involve in the neighboring group participation? Just remember, as I said, it should be a W shape. So here we have a W shape, but here we don't have a W shape. Okay, so first it get eliminated, and here positive charge, and this double bond goes and attacks to this like this. So this is the neighboring group participation. So this will be very fast in reaction, and here we'll get the final product. What we will get here is, if S state is the nucleophile, so this is the final product, but here we have a inverted product, and double bond will be like this. So this is about the neighboring group participation and anchimeric assistant in a bicyclic compounds. Just remember, these are not these are like in normal SN2 reaction we will be getting a inversion configuration, but here because of 2 times SN2 reaction is taking place, because of that reason the configuration will be retained, and the which groups will act as a in the neighboring group participation means the compounds which are having a electronegativity and lone pairs, they will act. And in this compounds, like if you take Narbonne compound, here C single bond C, I mean sigma bond is involving as a neighboring group participation, but here the pi bond is involving. Even this can also involve in the neighboring group participation. So this is about the neighboring group participation. And another thing I just want to say, these are the stereospecific reactions. Stereospecific means what? So whatever stereochemistry we have in the reactant, same stereochemistry will come in the product side also. So because of that reason we are calling these reactions as a stereospecific reactions. So if you have any doubts about this neighboring group participation, you can write in the comment box.